testing, testing. Okay. So if you can use this, just use this. Okay, so yeah. Uh, oh, oh, okay, that should be okay. So, mm, yeah, good morning. Mm, This one. Okay, I know that. Okay, previously we have introduced the vectors, like the scalars. So in kinematics in 2 dimensions, we need to use vectors to describe the quantities like velocity and the displacement and acceleration. So we need to know how to calculate the addition of vectors, and we use tail to tip, or we can use the other method like this, and subtract structure of vectors. Before we know how to calculate that, we need to know the negative vectors, and we use a triangle to help us to calculate the subtraction of vectors. But use a triangle is not usually it's not so easy to be calculated. So that's why we need the component form. So when we going to calculate the addition of the 2 vectors, we just need to calculate the sum of the components, and we calculate each component, and that's the result. And based on the vectors, we can define displacement. And we also use the components form and velocity and acceleration in components form. And for each component, that is exactly the same as a 1-dimension problem. So that's why we need the components form, because if we want to directly calculate the displacement or velocity or acceleration as a vector, that would be very complicated. But if you use the components form, that's just the same as what we did in previous chapters. But just for just like if for 2 dimensions, that should be 2 problems. And the equations in the 2-dimensional problem, that should be the same as 1 dimension. We just resolved it into components form. You can compare the equations for constant acceleration in one dimension, 2 dimensions. So you can see in 1 dimension and 2 dimension, that's almost the same, But we just use the components form. Like here, it's v is equal to v0 plus at, and here's vx is equal to vx0 plus axt. So, and for y components, we just change the subscript. So that means for kinematics in 2 dimensions, it's almost the same as that in 1 dimension. We just need to use the components form. So, just like this one, so the position of a particle as a function of time is given by this formula. And this is the x component, and this is the y component. We want to determine the particle's instantaneous velocity and acceleration as a function of time. So this is a motion in 2 dimensions. So when we solve the problems like this, we can just use the components form, and we take first order derivative of this part, that you will get this part, and this part takes first order derivative, you get this part, and then if you know v, you can calculate the acceleration. That's exactly the same as what we did in previous chapter for 1 dimension problem. What's the difference? You need to calculate the x components and the y components, and here x components and the y components. But for each component, that is the same as what we did in previous chapter. Just like, okay. Like here. So this is like x, actually is x, and this part is y, xt, say it's yt. So v, the velocity, should be equal to like vx I hat plus vy j hat. Here I and j, they are the unit components, and I hat means the unit vector in x direction, which means its length is 1 and the direction is in the x direction. So when we use the components form, so for each component, that's a 1-dimensional problem. So Vx should be equal to dx over dt. And you can substitute this part x into here, and you will get this part. And this is the y component. Vy should be equal to dy over dt. And the y is this part, and you substitute it into here, and you will get this part. And usually we don't need to calculate the magnitude of v or the exact direction of v. What's the angle of v? We do not need to do that, because the component form is equivalent to the vector form. So we use the component form. That's enough. We get its components. It's equivalent. that we get the whole vector, the direction empty. And for the acceleration, so that's dv over dt. So this part corresponds to dvx over dt, while this part should be dvy over dt. And vx should be this one, and the vy should be this part. And you can substitute this in this part here and this part to here. You will arrive at this two. So so that means vector kinematics or kinematics in 2 dimensions. We just resolve it into components and change these kind of problems into like several problems in 1 dimension. Okay, and for just we have showed you that all the equations in 1 dimension can be applied to 2 dimensions for each component. And when we compare this, the equations for the x and y components, that should be exactly the same as the equations in kinematics in 1 dimension. And this is for constant acceleration, and for all the other motions, that's the same. That's the same. Okay. So, okay, so in chapter 2 and 3, we investigated how the thing moves, like how they move. So that is kinematics. And in chapter 4 and 5, they're about what we call mechanics, or especially the dynamics. So dynamics is different from kinematics. Dynamics it tells us why the objects move like this. So the kinematics tell us how they move and help us to predict their motion. And dynamics tell us the reason why they move like this. So there's a difference between dynamics and kinematics. So Newton's laws can help us to understand the why they move like this. So yeah, sorry, I'm afraid it's missing. Okay. Why this? Okay. So this is a very famous book, which is called Principia. Uh, Originally, it's not written in English. It's used in Latin, like because at that time, Latin is the language that they use in academic world, like that. But at that time, English is not that widely used. So uh, this is a book uh, written by Isaac Newton, and it's a very famous book. And in this book, it describes tells about the calculus and the uh, Newton's laws and the gravitational laws. So in this chapter, we are going to investigate these topics about the force and Newton's laws, and how to solve problems with Newton's laws. So force, so is the it can it can help us how to explain why the things are moving like this. So we need the definition of force, but actually we do not know what is the force at that time. But we know, okay, I push this, I apply force on this object. We know we can describe this is a force, but we cannot describe the force with like scientific definition of force. We just know a rough image. What is a force? I push this, I will apply force on it. We know that is the force, but there is no scientific description of what is the force. So force in Chinese we call it li force. So dynamics investigate the connection between the force and the motion. So that is why we in Chinese we call dynamics 动力学. So 动 means motion, 力 means force. So 学 that means laws like this. So 动力学 dynamics, that's the connection between force and motion. The force in Chinese is 力. So it is a vector because we know the force as magnitude and direction. And the unit is Newton. So because in honor of this guy, Isaac Newton. So, but as we mentioned, what is a force? We know we push some object, that is a force, but we need a scientific definition. So in order to define the force, we actually need Newton's laws. So this is the first law. Every body continues in its state of rest or uniform speed in straight line as long as no force acts on it. So, now we know this should be correct, but at that time, not everyone agree with this. Not everyone. Just like here. They agreed with this continuous state of rest. They agree with this because even at that time, people know, okay, we do not push this object, it will not move, it will be at rest if I do not push that. So they agree with this, it will be at rest if there's no force on it. But they didn't agree with the second part. It can keep uniform moving in straight line with uniform speed when there's no force on it, because they believe, okay, if I do not push it, it will not move. If I let it move with constant speed in a straight line, I must push it. Then that means I apply the force on it. So they do not agree with the second part. It can keep moving with constant speed in a straight line. But what they didn't realize is that they ignored the friction. They didn't realize there is friction. So why I have to push it to make it moving in straight line with constant speed? That's because of friction. When it is moving, there's friction. So Galileo carried out an experiment to show the others if there's no friction, it can keep moving. So his experiment was like this: a slope and a ball fall from the slope, and he changed the substance here from very rough surfaces like the sands, and then switch this part to be glass. So he found that with sand it can move like here and here, but if we put the glass here, it will move to very, very far away. So Galileo concluded that, okay, if here is a surface with this very perfect surface, there's no friction, it can keep moving. So based on Galileo's experiments, Newton generalized this first law. So it can keep on moving if there is no force. So keep on moving at uniform velocity does not require let force. If it is originally at rest, we want it to move, we need a force. But if it is moving and we want it keep on moving like this, there's we don't need a force. We don't need a force to keep it moving. So that's what Newton's first law tells. And Newton's first law also tells us another thing which is called inertia. In Chinese, it is called 惯性, the tendency of a body to maintain its state. Everything has this inertia. It's just like a property of everything. Everything tends to keep its state of motion. Yeah, someone asked me, this law is almost impossible in life. Yes, almost, but it is true because when you are in this space, far from the planets and the stars, there's almost no force on it. So we can test that. And another thing is that as long as no let force here, no let force, which makes it possible in our daily life. Because here is no let force does not mean no force. No let force means there can be several forces on this object, but the sum is zero. Just like, for example, here is a rough surface, and I apply a force on it, and there will also be friction in the opposite direction if I let it move in this direction with velocity v. And if F is equal to the force I applied on this object is equal to the friction, the net force on this object should be 0. So that is equivalent to no force on it. So this object will keep on moving, and it does not require an extra force. So remember here, no net force does not mean no force. So there can be several forces on this object, and the net force, the total force on this can be 0. So this makes it possible in our daily life. Even on a rough surface like this, the friction is inevitable, but we can apply force on it, and this makes the net force can be 0. So this is possible in daily life. Okay, so inertia 惯性 is a property of everything. Everything wants to keep its state now. So everything wants to keep its state now, just not the motion, but just like if the environment is convenient for you, you want to keep that, right? And so everything tends to keep its state, and this is called inertia or 惯性. So okay, if we know the Newton's first law, actually we can explain this. A school bus comes to a sudden stop, and all the backpack here on the floor start to slide forward. So the question is, what force causes them to do that? And also maybe when you are on the bus, if there's a sudden stop, you tend to go forward, right? And you need to grab something so that you will not fall to the ground. So what force causes them to do that? Okay, so actually it isn't the force does it. According to Newton's first law, the backpack continue their state of motion. So the bus suddenly stopped, but you and the backpack will keep on moving. So they want to keep their velocity. They do not want to stop. So that's why they will move forward. But actually, they will not move with constant speed because of friction on the floor. So they will finally stop, but they will move forward. But if it is a frictionless surface, it will keep on moving. And that's the same reason why you will go forward. And you need the extra force to stop that. If there's no extra force, you will keep on moving. You will move forward. So it isn't the force that does it. It's the inertia. Everything wants to keep its state of motion, but maintain the velocity. So you will, even the bus stops, you want to move forward. You still want to move forward. Okay. So now we believe that Newton's first law should be correct. But someone may not agree with that. Still may not agree with that, just like here. Two guys, one is on the floor, on the ground, and the other for example, on a tree like this. And we can assume that here this surface is a smooth surface without friction. We can assume that. If we assume that, let's see what will happen when this train accelerate. So when this train accelerates, you can see here this ball moves to this guy. But when we consider this guy relative to this guy, it does not move, right? Still here, relative to this guy on the ground. So let's check this again. So originally the ball is here relative to this guy, right? And when it accelerates, it moves to this guy, but relative to this guy, still at rest. So for the guy on the ground, he believes that Newton's first law is correct because there's no force on this object and it keep at rest. So he believes that Newton's first law should be correct. But for this guy, he does not think so. He believes that there's still no force on this guy because it's smooth surface, and in the vertical direction, maybe the normal force and the gravity they balance each other. So there's no net force on this object. But why originally it is at rest and now it is moving? Why it start to move toward me? So the guy on the train, he does not believe the Newton's first law is correct. So that means that Newton's first law does not always hold. There should be requirements, or Newton's first law holds only in special substitutions, like this. When, or in what kind of requirements is this the reference? We can see the difference between these two observers as they choose the different reference. And this guy choose the ground as the reference. And this guy choose this accelerating train as the reference. So that's the difference. So that means in different reference frames, Newton's first law will not always hold. It holds only in initial reference frame. The reference frame in which the Newton's first law holds is called initial reference frame. Or we can, so this definition cannot help us to determine which reference frame is initial reference frame. So we need this explanation to help us to determine which one is initial reference frame. The reference frame fixed on a body which has no acceleration or has no force on it. No net force would mean no net force. Or net force on it is 0. For example, here in this classroom, the desk originally at rest, right? The desk at rest. The desk has no acceleration relative to the ground, and the net force on this desk should also be 0. And if we choose this desk as a reference frame, that is a initial reference frame. And if we choose the ground as a reference frame, that is also an initial reference frame. But if you choose the train, that is not, because the acceleration of this train is not 0. So that's the initial reference frame. And usually on the Earth, we can choose the Earth as an initial reference frame for most of the problems. But when you are dealing with the L movement in the atmosphere, you cannot treat the Earth as a reference initial reference frame because it's spinning. But in the most of the case, if we when we discuss the motion of the object on the Earth, on the surface of the Earth, we can treat it as a initial reference frame. So Newton's first law is only valid in initial reference frame. So, but there can be several reference frames in which the Newton's law holds. This reference frame, this initial reference frame is not the only one. There can be several initial reference frames. Any reference frame that moves at a constant velocity relative to an initial reference frame, that is also an initial reference frame. So that's why if we treat the Earth as an initial reference frame, the desk at rest on the surface of the Earth, it is also an initial reference frame. So you can choose any reference frame which moves at a constant velocity relative to the Earth. So anyone is okay. It depends on which one you feel that's convenient. And the reference frame in which the Newton's first law does not hold, that's long initial reference frame. For example, that train, some object is moving with non-zero acceleration on the surface of the Earth, or something is rotating. Something is rotating, and you choose that object as a reference frame. That is not an initial reference frame. Something is rotating and something is accelerating. They cannot be chosen. They are not be chosen as an initial reference frame. Okay, that's the first law. The first law tells us everything wants to keep its state. But if everything wants to keep its state, that's not so good because sometimes we need them to change. So if you want to change the state, just like if it is moving, you want to stop it, we need a force. So Newton's first law is about the case when there is no let force. But what if there is force? There can be several forces on this object. So that's something need to be explained by the second. But before we discuss the second law, we need to discuss, before that we need to know something like the mass. The mass in Chinese is called 质量. According to Newton's original explanation, he defined the mass as the quantity of matter. And what does the quantity of matter mean? It actually means the measure of inertia of a body. So why the mass means the quantity of matter or the measure of inertia of our body. So that's reasonable because according to our daily life, if something very heavy and it is moving, you want to stop it. It's very hard, right? But if something light and is moving with same speed, you want to stop it, that would be easier. So that means the heavier things, it's not so easy to change its state of motion. But light things, you can change its state very easily. So maybe we know heavy means more matter. That means heavier object has greater mass, and it is not easy. It's not easy to change its state of motion. And inertia means they want to keep its state of motion. It's easier. It's not easy to change. Means it's easier to keep, right? It's not easy to change. It means easy to keep. So that means heavier object tends to keep its state of motion. That means heavier objects have greater inertia. So that's why we say the mass is the measure of inertia. It's the measure of inertia. And you need to know mass is different from weight. Mass is the measure of inertia, while weight is a force. It's a force the Earth's surface of our Earth on this object. Okay, let's take a rest. We'll go on after 5 minutes. And this is the attendance for the fourth one and the next one. So you can also use this week because according to the SIE, they ask us to do this twice each time. So this is for the second time. So we are asked to check the attendance twice each time, right? So, and this is for the second time. If you haven't do that, so be quick. So you can do that quick. Okay, so to get this. Okay, put it back. Okay. You can do this after, like, I give you 1 or 2 minutes. Okay, so let's go on. Okay. So mass in Chinese we call it 质量, but weight is different from mass. Weight in Chinese is called 重量. So mass and weight, they are different. Mass is the measure of the inertia of a body, while weight is the gravitational force on it near the surface of the Earth. So this is a force, and this is not a force. And they do not have the same quantity. For example, if we use m, okay, sorry. So if I use n, you indicate mass. And near the surface of the Earth, weight is equal to mg. G is the acceleration of free fall object near the surface of the Earth, and g is equal to 9.8 meters per second squared near the surface of the Earth. So these two, they are not the same. Mass m and weight is mg. Weight is a force, while mass is the initial of the measure of the initial of the object. So that's why we all we can call it initial mass because it's the measure of initial of a body. But usually we call it mass for short. Okay. After we defined the mass, we can go a step further. That's the Newton's second law. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of the acceleration is in the direction of the net force acting on this object, and we can use a simple equation to help us to describe this Newton's second law, which is F is equal to ma. Maybe you are familiar with this equation. The force, this is the force, and is equal to the mass times the acceleration. So the force is proportional to the mass, and the acceleration is proportional to the force, but the acceleration is inversely proportional to the mass. So and they have the same direction. If we write this equation in a vector form, we can put an arrow on this force and put an arrow on this acceleration. That means, and m is a constant for a specific body, so that should be the same direction. But this equation actually is not the original form of Newton's second law. So the original description by Newton is something like this. The alternation of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. So here, the alteration of motion, Newton, when Newton explained this, he said it should be equal to mv, the mass times the velocity. That is called the alternation, the change, the alternation of this alternation of mv. So alternation of motion is alternation for mv. So if we use the language of calculus, this force should be equal to dmv over dt. It's different from this one. This one is equal to m dv over dt. So this one is equal to this one only when the m does not change, the mass does not change with time. So this one is more general, while this one is practical in our daily life. So this is the equation for Newton's second law in 3 dimensions. In 3 dimensions, we can use the complex form because force is a vector. We can use a complex form. That's the second law. So second law, actually, it helps us to know what is the force because we have defined the mass, and we already know what is the acceleration. So according to Newton's second law, what is the force? Force is the mass times the acceleration. The mass times the acceleration is the force. So that helps us to define the force. And now we do not use this to help us to measure the force. Usually we use a spring to help us to measure the force. And if we know we can measure the force, and still this F is equal to FA, can help us to measure the mass. So why we need to use this equation to help us to measure the mass? Because maybe when you want to measure your mass, on the surface of the Earth we have certain equipment, right? It does not based on this equation, because we know on the surface of the Earth the mass is proportional to the weight, right? So actually we are measuring the weight on the surface of the Earth. But this method will not work when you are in the space. So in the space, we need to monitor the mass of the astronaut to make sure they are healthy. We must monitor the mass of the astronaut every day. But on the in this space, the weight meter will not work. You put anything on that weight meter is zero. So in this surface, how can we know the mass of the astronaut? So we actually had a certain device, if this is some device and this is something, and something like a device like this, and put the astronaut here, and then we release this part, and it will move in this direction. And actually, this device can apply a constant force through this part on this astronaut. And we measure the acceleration. Then we measure the acceleration of this astronaut. We know this constant force, and we measure the acceleration of this astronaut, and this can help us to calculate the mass. So that's how we measure the mass of the astronaut in the space. And this is based on Newton's second. We do not use this device on the surface of the Earth because we can use weight. We can measure the weight, but in the space we cannot measure the weight, because that you use a weight meter to measure anything that's zero. Because in this space that's zero weight, right? Okay, that's the second law. And the third law, and maybe most of you are familiar with this, is whenever one object exerts a force on a second one, the second object exerts an equal and opposite force on the first. So if we use a equation, that's F12 is equal to minus F21, which means in the opposite direction. So this one is very simple. So, and you all know this, so we will not focus on this one. Okay, so we have introduced three laws, and when we want to apply these laws to the real problem, we need to know the different kind of forces, the feature of the forces. If we want to use that, for example, the second law, F, so the force. So we want to know the feature of each force so that we can use the right equation instead of a simple letter F in that equation. So in this section, we are going to investigate the forces in mechanics. We start with this one, gravity. The gravitational force and gravity. So we know the equation, gravitational force. The force is equal to G m1 m2 over r squared. This is a gravitational force. And gravity, we mean the almost gravitational force near the surface of the Earth, but slightly different. But for example, the gravity actually it consists of not only the gravitational force, but also the effect of the rotation of the Earth, of the spinning of the Earth. But usually we can write it like this: gravity near the surface of the Earth, m is equal to mg, but only near the surface of the Earth. Only near the surface of the Earth. So, and when we are very close to the surface of the Earth, these two is almost the same, the gravity and the gravitational force. When on the surface of the Earth, they are almost the same, but slightly different because of the spinning of the Earth. So on the surface of the Earth, these two, we can treat it almost the same as an estimation. So, but when we talk about gravity, we know F is equal to mg, but according to the Newton's second law, if the object has acceleration a, F is equal to ma. For a free fall object, these two should be the same force. So if these two are the same, we can arrive at here. Ma is equal to mg. Then we can cancel the m's, so that a is equal to g. But according to Newton's second law, this m, it means the measure of the inertia. But according to this equation, this is the gravity. So according to this equation, this m is the measure of gravity. The heavier the object, the greater the m, because g is constant. So which means these two m's, actually they are not the same. The m on the left-hand side is the measure of the inertia, while the m on the right-hand side is the measure of gravity. Actually, we should not use the same sign. So we call this the initial mass, while we call this one gravitational mass. There are different physical quantities, but in our daily life, when we cancel these two, it's a correct conclusion. It has been tested. Okay, what does this mean? This means the number of the pages for the hard version of the book. But if you do not use the hard version of the book, you can ignore this. Okay, are the UMs happen to be equal? Because they are equal to each other. Because this conclusion is correct. It has been tested several times, many times. So Einstein says, no, it's not happen to be the same. They should be the same. They are different quantities, different physical quantities, but they should have the same value. So that's something interesting. So this is called the principle of equivalence. This is called the principle of equivalence. It's one of the fundamental assumptions of the general theory of relativity. So we'll discuss this later in next semester when we discuss the relativity. So gravity is one of the forces. Why we explain gravity first? Because you can never escape from gravity, right? You will never escape from gravitational force. No matter how far away the two objects are, there will be force between them. So no matter how far away your objects are. So there will be gravitational force between them. So that's why we discuss this first. It's a universal gravitational force. So you cannot escape from this. So why we say it's universal, because you cannot escape from that. And Newton, at that time, Newton realized that something is falling and something is go around the Earth, like the moon, and the apple fall from the tree to the Earth. Actually, that's the same kind of motion. So why they are actually the same? So we can explain that. So why they actually same? Because the force on them same. So just like this is the Earth, something apple fall to the Earth, and the moon go around the Earth. According to Newton, these two motions should be the same. What's the difference between these two? Okay, we can see it like this. When you throw something, like when you throw something with greater speed, it will go further, right? Okay, that's on the flat surface, but our Earth is not flat, right? It's like a spherical surface, like this. And if you throw something, it will go further, and throw with greater speed, it will go even further. But it's a spherical surface, a curved surface. So if we throw it with very large speed, it will fall, but it will not on the surface because it's a curved surface, right? And it will go on moving. It want to fall, but it cannot fall. It will go around the Earth. So the difference between the apple and the moon is that they have different horizontal directions, horizontal velocity. It will directly fall to the Earth if there's no if it is zero velocity, it will directly fall to the Earth. But with small velocity, it will fall to some place further. And if you have enough velocity in horizontal direction, you can move around the Earth. So that's why if you want to launch a satellite, you need to make sure it has enough speed so it can go around the Earth, not fall to the Earth. If the speed is not enough, no matter how high we release it, it will fall to the ground. So that's the difference between the moon and the apple. They are different in the horizontal speed. Horizontal speed. Okay, so that's the gravitational force. And there are other forces like the force on the spring. If the spring originally is like this, and we put it here, a displacement of x, the force is equal to minus kx. And x means the displacement relative to the equilibrium. Where it is minus sign means the force is in the opposite direction of the motion. So this is one kind of elastic force, the force caused by the change in the shape of solid. When you change the shape of this spring, it wants to go back to its original position. So in this case, the force appears because of this. And the elastic force is not not only the force in the spring, but also like this. If you use a rope to drag this block, this tension, the tension in the rope is elastic force, is a kind of elastic force. Because you use this rope, the rope want to be longer, but it will go back to its original length. So that's why the tension appear. And the normal force, the force on this block due to the contaction between the force and the surface, the normal force is also elastic force. So normal force, tension, they are also elastic forces. So that's there are many kind of forces. There are elastic forces. The force caused by the change